All right, here's 9-1, day 2. So in day 1, we introduced sequences. Just kind of the basics with the understanding we're going to do a lot more with them in the next few sections. Similar deal here, we're going to introduce the idea of a series, just the basics. We'll deal with them a lot more in the sections that are ahead. Okay? Remember this, I'm going to jump right into the notation here. This big fancy symbol here means sum. Okay? So what's going on with a series is you add up the terms as you go. Right? So a sub I, that's going to be like a formula that we saw. And it's going to describe some kind of sequence. Okay? But now if I'm going up to n, right, a sequence would just describe what the nth term is. We did that a lot in the first day where you just plugged in a number for n and then you found that term in the sequence. A series adds up the first n terms. Okay? A series adds up the first n terms. Okay? The number written below the sum is going to tell you where to start, and the number written above the sum is going to tell you where to stop. How many terms do you want to add up? Now, we're not going to do anything today really fancy with series, so we'll have to be limited to fairly small sums. But it won't stay that way. We'll see some formulas that allow us to do some pretty interesting things to put together really, really large sums really efficiently. But not today. Let's dive into some examples. You'll see each of the examples I'll do down here fit the definition perfectly. Okay? So 3i is my sequence. Okay, so it means for the first term of that sequence, put in 1 and then multiply it by 3. Put in 2, multiply it by 3. For the third term, plug in 3. Fourth term, plug in 4. For the fifth term, plug in 5. Okay? Now this sum is going to be a single number. Okay? As I simplify these, again, had I been talking about a sequence, the first term would have been 3, second would have been 6, third 9, fourth 12, fifth 15. But a sum, okay, so focus on that fifth one. If it had been a sequence, the fifth term in this sequence 3i is 15. The sum, I want to add up the first 5. So my final answer for this one is 45, because I added the first 5 terms together. Now check out the next one. Look at where it starts. Series don't have to start at 1. That number on the bottom will say, okay, start with 3, and now let's go up to 6. So I'll do 1 plus 3 squared. 1 plus 4 squared. There's 5. And there's 6. Okay? That would be 10. Second, well, that really is the fourth term, would be 17, because I'm adding up 3 through 6. Third term is 10. Fourth term is 17. The fifth term is 26. The sixth term would be 37. I want the sum of those 4, okay, and I'd get 90. Again, keep in mind here, this is really, we're just looking at the idea, right? This isn't a very efficient way to do a sum. Okay, that's going to change in the days ahead. Do you get the idea of the notation and what we're doing when we talk about a series to add up those particular terms? Okay, here's one with a factorial. It's going to start at 0, and I'm going to go up to 8, so this one will be a little crazy. 1 over 0 factorial plus 1 over 1 factorial. I mean, there's the sequence right here. It's 1 over I factorial. 2, 3. Do you remember where I get to stop? It's 8. That number on the top tells me I can stop at 8. Whew. There's a lot going on there. Now check this out. That's 1 plus 1 plus 1 over 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. Now I want you to see on this one a couple things. Factorials start to increase really, really fast because now 720 gets multiplied by 7. So 7 factorial is 5,040. 8 factorial is 40,320. Now, I don't want you to crunch those numbers yourself, but I did want to show you that this one's kind of interesting. That adds up to right around 2.718. There'll be more to it. But if you think back to logarithms or natural logs of base e that we saw in Chapter 3, that particular series adds up to e, 1 over I factorial, which I think is kind of fun. All right, all we're saying here is that a series does not have to be finite. Those ones that we just saw, they all were. I think the most we added up was 9 terms. The first one we did 5, the second one we did 4, the last one we did 9. There does not have to be any kind of limit. Now, this is where series can get really, really interesting. Okay, you would think if you keep on adding up terms forever, that don't the terms always just add up to infinity? Right? Like conventional logic would suggest that if you keep adding numbers forever, there's no limit as to what they will add up to. And the answer is no. That very, very often is not the case. Okay, it's very common that for a particular sequence, it depends on the particular pattern of numbers that you have that will be described in the series. I'll show you one right now. So it's going to be the same one, but let's compare the finite and then the infinite. Okay, this is, so first of all, the sequence is 3 over 10i. 3 over 10 to the first, 3 over 10 to the second, plus 3 over 10 to the third. Okay, this would be 0.3 plus 0.03 plus 0.003. Okay, so that would add up to exactly 0.333. So if we keep following this pattern that basically every time we take 10 to a higher power, here's the first 3 that I found. The fourth term would be to add 0.0003. The fifth term would look like that, right? And this would just continue. And as long as you kept adding terms to the sum, you just keep adding decimal places of 3. We could describe that more quickly as 0.3 repeating, or 1/3. Okay, so for that particular sequence, you could go and add terms forever. Okay, if you did keep adding terms forever, they would add up to a relatively small number of just 1/3. Okay, I'm not going to work this one all the way through, and I don't think you need to either. it's a context, right? We're not, contextual questions, we're not doing anything really fancy yet. What I'd be looking for here is that you recognize that this is just a sequence question. This sequence describes the population growth, okay? And it wants, you know, for 5 years, I'm just going to do 2 of them. If you want to do the other 3, you can. Okay, from what it describes, A sub 19 would be the population estimate in 99. Well, that would be 226.9 plus 205 times, this is kind of going back to the first day, 19 goes in for N, and you would get 278.5, and it says that those units are in millions. Okay? In fact, I don't think I need to do the second one. It's asking for 5, and again, I don't really care which ones you do, if any more. If we were to complete this, I think the important thing you need to understand would be that we have four more terms in the sequence, because the sequence would be the population estimate for each year. Okay, A sub 20 up through A sub 23. That's what you would be going on to find.